Hello all. In today's session, we will talk about the next topic, evaluating the performance of the model. So far we have established a baseline model and also performed pre-processing of the data. So now it is the time to train the model as well as measure its performance. So once the training is complete, what do? Is we determine what are the bottlenecks or diagnose which components are performing poorly and determine whether that performance or the poor performance of the model is due to overfitting or might be due to underfitting or there might be some defect in the training data. So we will be discussing all these three drawbacks which results in the poor performance of the model, that is overfitting, underfitting and defect in the training data. Anyways, we have talked about these two terms, overfitting and underfitting, in the previous sessions. Let us just recap. Underfitting is when the model is very simple. As it fails to learn, it performs poorly on the training data. So it fails to learn all the data which is provided for training. Coming to overfitting, it is the model when the data set is too complex. So when complex data is provided, instead of learning, the model will try to memorize the entire training data. So as it is memorizing but not learning, it will perform well on this training data but will fail to generalize when tested with some new data. So here the model is trying to capture or memorize all the data points which are provided for training. Now our aim is to build a model which is just right for the data. That is, it is neither too complex, that is my model what we are designing is neither too complex nor too simple. If it is too complex, it results in overfitting, and if it is too simple, it will cause underfitting. To diagnose these two drawbacks, that is underfitting and overfitting, we will be focusing on two parameters, that is training error and validation error. When you run your program, you can see at the output for each epoch, the loss, training accuracy and training loss, validation loss and validation accuracy will be displayed for the number of epochs you have mentioned. You can see here in the first epoch, second epoch and so on. Now what do you find here is, if the model is performing well on the training data and does not perform well, that is poor performance on the validation data, then I can say that the model is overfit. And if it does not perform well on the training data, performs well on the validation data or the test data, then I say that it is underfit. So we will be talking about these two, overfitting and underfitting. Before moving into underfitting and overfitting, let us consider a term called as base error rate. So based on the human level performance, we will find out this base error rate. Now what is this base error rate? It is representing the best possible error our model can achieve theoretically, or I can say that it is the lowest possible error rate for a given classification problem. Since humans are usually very good with the visual task, we can use human level performance as a proxy to measure this base error. Now to understand this statement, let us consider a simple task like classifying the image of a dog and cat, and humans are very accurate in doing the classification. If an image of a dog and cat is provided to a human, he will easily classify that given image is either dog or cat. Now if I say that, for example, the human error rate for this task is around 0.5%, then I would like to compare, I will design a model and I will train this model and I will compare the training error of this model with this value, that is 0.5%. And the model what I have designed, for example, for this model I got the accuracy as 95%. Then I can say that this model what I have designed is not having a satisfying performance, because I am comparing the accuracy of the model what I have designed with this 0.5% error, that is 99.5% humans are accurate taking this accuracy as my starting point or a bottleneck, I will compare the accuracy of the model what I have designed. On the other hand, for example, we are working on a more complex task for the humans, like we will ask a human to build a medical image classification. So images are given, medical images are provided to human and asked to classify those images. Here I can say that the human error rate, they are not accurate in classifying the medical images. So for example, I say that here the error rate for such classification is somewhere around 9.5%. This is the model what I have designed. I have trained the model and calculated the accuracy. I got 95% accuracy. Now if I compare this 95% accuracy with this much of error, that is 5%, then I can say that this model is doing a very good job in classification. So what we are doing here, we are making use of the human level performance as the base to find out the base error rate. So I can say that no matter how sophisticated and advanced model we are designing, taking baseline model into consideration, this base error rate will indicate the best accuracy you can achieve, because it will find the uncertainty in the data. It will find whether there is any overlap in the data or not. In the first, we have talked about underfitting and overfitting. Now we will be plotting the training and validation error. You can see here three graphs here. The blue line represents the training loss and the red color line in the graph represents the validation loss. So instead of looking at the training data output and comparing with the numbers, we will find out why this overfitting and underfitting is happening by taking these two parameters into consideration. Look into the first figure. What do you see here? The network improves the loss value on the training data, but will fail to generalize on the validation data. So you can see here, as I am increasing the number of epochs, the loss is getting reduced here, but there is no change in the validation data. So this is a form of overfitting in my first graph. Now look into the second graph. What do you notice here is it is trying to learn all the data points, or it is trying to memorize all the data points which are provided for the training. That is, this figure shows that the network is performing poorly on both training as well as validation data. So in this case, I can say that the network is not learning, because I don't have any either increase and decrease in the loss. It is not learning. You have a constant loss value through each epoch. Coming to the third figure, this figure shows that the network is doing a very good job for learning the training data as well as for the validation data. This means there is a good chance that the network will have good performance on the test data as well. Now we'll talk about the next topic called as improving the hyperparameters. So we will be talking about either we need to collect more data so that the performance of the model what we have designed is increased, or we need to go for tuning the hyperparameters. This word called as hyperparameter, we will be studying it in the next session. Let us talk about these two parameters which are used or which will be discussed when we talk about underfitting and overfitting. That is, when do we need to go for collecting more amount of data, and when do we go for tuning the hyperparameters to increase the performance of our model. That will be discussed here. So to have these two parameters into consideration, these are the points we need to consider. Determine whether the performance on the training set is acceptable as it is or not. Then we will visualize and observe the performance of these two metrics, that is the training accuracy and validation accuracy. If the network yields poor performance on the training data, that is, it is not performing well on the training data, then it is a sign of underfitting. There is no reason to gather more data here, because it is not learning anything from the data. Though I increase the data, it will not learn anything from the data, because the learning algorithm is not using the training data that is already available. Instead, what do we do is, instead of increasing, we will try to tune the hyperparameters or clean up the training data. So we are improving the model's ability to learn by increasing the model complexity. We are improving the model's ability here to learn from the existing data rather than acquiring more data. Coming to this, if the performance on the training set is acceptable but is much worse on the test data, then the network is overfit. So when you have overfitting problem, we need to collect more amount of data, and when the model is underfit, we need to tune the hyperparameters. These 2 points you need to remember. When do we need to increase the data and when do we need to tune the hyperparameters? So underfitting, we need to tune the hyperparameters, and when the model is overfit, we need to collect more amount of data. So when we are evaluating the model performance, the main goal is to categorize the high level problem. If it is data problem, spend more time on data preprocessing or collecting more data. And if it is learning algorithm problem, then try to tune the networks. Next, we'll talk about parameters and hyperparameters here. You shouldn't get confused with these two terms, parameters and hyperparameters. They are not same. Parameters, I can say that these are the variables that the network will update. For example, weights and biases. And hyperparameters, these are the variables that we will set and tune. That is, these are the variables that are not learned by the network. The data scientists will set these hyperparameter values before training the model. And example, I can say that learning rate will be decided by a data scientist, and the number of epochs required also will be decided by a data scientist. All these can be considered as examples of hyperparameters. Though both are variables, parameters are updated by the network itself, and these are the variables that are set by a data scientist. Hyperparameters are the variables that we set and tune. Parameters are the variables that the network updates with no direct manipulation from us. Parameters are variables that are learned and updated by the network during training, and we do not adjust them. Examples are weights and biases. In neural networks, parameters are the weights and biases that are optimized automatically during the backpropagation process to produce the minimum error. In contrast, hyperparameters are variables that are not learned by the network. So this is just a pictorial representation of the hyperparameters. Tuning of hyperparameters means what? We are varying the values of those hyperparameters. So I can consider these hyperparameters as knobs whose values can be varied, and our job here is to set and tune the knobs to yield the best performance of the model. So I can vary the learning rate, I can vary the epochs, number of hidden units involved in the network, as well as how many batches of data should be used for training the model. All that, these are the hyperparameters that will be decided by the data scientists. So this is end of today's session. In the next session, we will talk about neural network hyperparameters. Thank you.